The Pythagorean Theorem is one of the most famous theorems in geometry. It states that for any right triangle, the square of the hypotenuse equals the sum of the squares of the other two sides. But how do we know that's true for any right triangle? I mean, we can't test it out for the infinitely many possible right triangles there are, so there must be some sort of general proof. You may have been taught that if you draw three squares with side lengths A, B, and C, the total area of the squares of side lengths A and B will be the same as the area of the square of side length C, which means that these two squares would fit perfectly into the C square. But that's not really helpful because there's no way to fit them perfectly inside without cutting them up in some non-general way. Fortunately, there are many proofs that do work generally, and in this video, we're going to go through three of my favorites. This proof is arguably the most famous. Let's start by drawing a big square, and inside the square we'll draw four identical right triangles, like this. Let's say that the shorter side of each triangle has a length of A, the longer side of each triangle has a length of B, and the hypotenuse of each triangle has a length of C. Now, this orange shape looks like a square of side length C, but how do we know it is a square? Well, the sides come from the hypotenuses of each of these triangles, which are all C, but to qualify as a square, it's not enough for all sides to have the same length. For all we know, this could just be a rhombus. We need to be sure that each of its angles are 90 degrees. So how do we do it? Well, let's zoom in on one triangle. This angle is obviously 90 degrees, and let's call the other two angles X and Y. We know that the sum of the angles in any triangle is 180 degrees, and if we subtract 90 degrees from both sides, we are left with the statement that the other two angles, X and Y, are complementary. Now let's put that triangle back in and take a look at the one above it. This angle is clearly a right angle, but what about the angle between B and C? Well, let's take a look at our other favorite triangle. We can see that the angle between its B and C is what we called Y, and since they are congruent triangles, this angle must also be Y. Now, what is this angle here, the one that I've decided to call Z? We'll notice that all these angles X, Y, and Z lie on the same straight line. This means that their sum must be 180 degrees. Remember from our previous observations, we know that X plus Y is 90 degrees, so we can substitute 90 in for X plus Y. Subtracting 90 from both sides, we find that Z, the angle of this orange shape, is in fact 90 degrees. And you can use this logic for all the other angles of this orange shape, proving that the orange shape is in fact a square. And since it has side lengths of C, its area is C squared. Now here's the fun part. Let's rotate and move these triangles like this, preserving the empty space inside the square. This creates two new squares. The smaller square has side lengths of A, which comes from the short sides of the rearranged triangles. This means that the square has an area of A squared. The larger square has side lengths of B, which comes from these sides of the triangles. So, the area of this square is B squared. Since all we did was just rearrange the triangles, the total empty orange space remained the same. So this gives us the Pythagorean theorem, C squared equals A squared plus B squared. Our next proof was discovered by US President James Garfield. We start by drawing a right triangle, and once again we'll call the short leg A, the long leg B, and the hypotenuse C. Then we make a copy of this triangle and we shift it and rotate it by 90 degrees so it ends up here. Next, we'll draw a line like this, forming a third triangle. These three triangles together form a trapezoid. Now, what is the angle between the two hypotenuses of the blue triangles? Pause the video right now and see if you can figure it out yourself. Alright, I hope you've tried to figure it out yourself because what we're about to do should look very familiar. Let's zoom in on one triangle, and this angle is the right angle of our right angle triangle. And we can use the same logic as before to deduce that the other two angles are complementary. Putting that triangle back in, we can say that these three angles add up to 180 degrees, and from there deduce that the angle of our orange shape is 90 degrees. This means that our orange triangle is a right angle triangle. Now, what is the area of this trapezoid? Well, the area of any trapezoid is 1/2 times the sum of its bases, which in this case are B and A, multiplied by the height, which in this case is B plus A. Remember that this trapezoid is made of three triangles, so its area is the sum of the areas of each triangle. The area of this bottom triangle is half BA, the area of this upper triangle is the same thing, and the area of this orange triangle is half C squared. First, let's factor out the half on the right side of the equation. And that BA plus BA in there, it just simplifies to 2BA. Notice these halves on both sides of the equation. If we multiplied both sides of the equation by 2, these halves would cancel out. On the left side, we're left with B plus A whole squared, which simplifies to B squared plus 2BA plus A squared. And we can subtract 2BA from both sides, leaving just the Pythagorean theorem behind. B squared plus A squared equals C squared. Our final proof of the day is Indian mathematician Bhaskara's first proof of the Pythagorean theorem. Yeah, he had another one, because apparently one proof was just too normy for him. Anyway, once again we start with a right angle triangle, but this time we arrange 3 copies of it like this. The space in the center happens to form a square, but we actually don't need to worry about that. As a sidetrack, can you prove that the orange shape is a square? Try it. Anyway, as usual, let's say that our short length Let's say that our short leg has a length of A, our long leg has a length of B, and our hypotenuse has a length of C. Because each of these triangles has the same hypotenuse, C, it seems like our overall shape might be a square. But remember, we need to make sure each angle is a right angle. Once again, pause the video right now and see if you can prove it yourself. Alright, I hope you've tried to figure it out yourself, because what we're about to do should look very familiar. Let's zoom in on one triangle, and this angle is the right angle of our right angle triangle. And we can use the same logic as before to deduce that the other 2 angles are complementary. Now let's put that triangle back in, and this time we're going to take a look at the one next to it. This angle is clearly 90 degrees, but what about the angle between the short leg and the hypotenuse? Well, let's take a look at our other favorite triangle, and we can see the angle between its short leg and the hypotenuse is what we called x. And since they are congruent triangles, this angle must also be x. Now what is this angle here, the one that I've decided to call z? Well, notice that z is just the sum of x and y. And remember that x plus y is 90 degrees, so z must also be 90 degrees. Of course, we can do this for all the other angles in our shape, and we'll find that each of the angles are right angles. Since we know that this shape is a square of side length c, we also know that its area is c squared. Let's make a copy of this shape, and we'll move these triangles to a new home, like this. If we draw a line here, we end up forming 2 new rectangles. The small rectangle has a side length of a, which comes from this triangle right here. And what's the length of this side? Remember that this side comes from this triangle leg from over here, which is a, so this line is also a. Lo and behold, it turns out our rectangle was actually a square all along, a square of area a squared. Now, this side has a length of b, which comes from this triangle over here. And what about this side? Well, this side used to be the leg of this triangle, which is b, so this side must also be b. Well, turns out our blue rectangle was also a square all along, and this one has an area of b squared. The key is that the overall area of the shape on the left, which is c squared, is the same as the overall area of the shape on the right, which is a squared plus b squared. This gives us, for the last time in this video, the Pythagorean theorem. And that's it! Those are my favorite proofs of the Pythagorean theorem explained. If you enjoyed the video, don't forget to hit that like button, and definitely remember to subscribe so you don't miss the next upload. What do you want to see in the next video? Drop your suggestions in the comments down below. Anyway, thanks for watching!